In this episode of TLDR, we're covering free body diagrams and the component nature of forces. During your physics studies, you have likely come across free body diagrams already. Simply put, free body diagrams show the magnitude and direction of all forces acting on an object. We can look at an example as follows. A skydiver is in freefall after jumping out of a plane and he has reached his maximum velocity. So there are two forces acting on the skydiver, gravitational force and the force due to air resistance. We can either draw the free body diagram on the skydiver with our gravity force acting down and our air resistance opposing his motion, or you can replace the skydiver with a single point and draw the forces acting from this location. This simplifies the image for when we're adding vectors in the future. When we look at forces in our physics course, we are only looking at forces in a two-dimensional plane, otherwise known as the x and y direction. In the last episode, we discussed how vectors have both a magnitude and direction in which they act, but we didn't discuss how this relates to forces outside of a single dimension. What we must understand is that all vectors, such as force or velocity, always have an x and y component in which they act. This is best shown using an example. Let's say you throw a ball at 10 meters per second at an angle of 30 degrees to the ground. We know that since this ball is travelling at an angle, it must have both a horizontal and vertical velocity component. We will call these v horizontal and v vertical. We can draw our velocity on a triangle diagram and then use our trigonometry laws to split our original velocity into these two components. Applying our trigonometry, we know that the vertical component, vv, is equal to our original velocity, v, multiplied by the sine of our angle, which is 30 degrees. From this, we can calculate that our vertical component of our original velocity is 5 meters per second upwards. Now the horizontal component can be calculated in the same way. We have VH is equal to our original velocity v multiplied by cos 30, which is our angle. This is equal to 8.66 meters per second and its direction is to the horizontal plane. So we can see that we have resolved our velocity into both the horizontal and vertical component. Now we must remember that every vector in the future can also be resolved in this way. We can now look at how the addition of forces occurs. We already know that if we have two forces acting in the same direction, we can simply add them together to find the net force. But what happens when we have two forces acting in different directions? Let's say you and a friend are trying to move a large box. One of you is pushing from the left with a force of 300 newtons, and one of you is pushing from the bottom with a force of 400 newtons. We can now draw a free body diagram of this situation. When we add our vectors together, we must follow the tip to tail rule. That is, we can move our force component so the tail of one acts from the tip of another. We can now see that like our ball, the resultant force is calculated by the summation of the forces in the horizontal direction and the vertical direction. We can draw the resultant force to complete our triangle, and since this triangle is right angled, we can use Pythagoras and trigonometry to find the resultant force. So we apply Pythagoras and we find the formula in this case is equal to F net squared is equal to F vertical squared plus F horizontal squared. We can find the magnitude of our net force is equal to 500 newtons. Now to calculate the angle in which it acts, we will apply trigonometry and use our tan rule. Our angle theta is equal to the inverse tan of 400 divided by 300. We find that our resultant force acts at an angle of 53 degrees, so our resultant force applied to the box is 500 newtons at an angle of 53 degrees. Okay, so let's recap on what we've covered today. We can now draw free body diagrams of simple scenarios, calculate the vertical and horizontal components of vectors, and determine the resultant force given a horizontal and vertical component. I recommend you go and watch our super short calculation video to test your knowledge using these new principles. Otherwise, If there's something you'd like us to cover in the future, leave a suggestion down below. Thanks for stopping by. See you next time.